Welcome, everybody. Hello from Mainz. I'm Albert Gräf from the Department of Music Informatics at the Johannes Gutenberg University in Germany, and the topic of my talk is Pd-Faust Mackie control. So this is about PD, pure data, Miller packets, real-time multimedia environment, and Faust, Graham's functional DSP programming language, which lets you write DSP modules for various environments, and one of these environments is PD. And this talk is about controlling these modules in a convenient way. So the gist of this is that we want to do automatic mapping of all Faust MIDI controls with a device which speaks the Mackie Control Protocol, or MCP for short. You can find this software on GitHub. Just click on the link in the slides, and this currently runs using my Pd-Faust package, which is a bit hard to install, so I'm currently planning to port this over to Pd-Faust Gen 2, which is based on Pierre Gillot's Pd-Faust Gen package, and is much easier to install, but this is still in the future, so I'm presenting the software as it is available now. I pre-recorded this, but of course I will be available in Big Blue Button later to answer all of your questions. Okay, so let's get right into it. Okay, just to be clear, I'm talking about these kinds of devices which look a bit like mixers and which you can use to control your DAW software, and the original one, of course, was the Mackie control. This is the latest version of that, and but there are plenty of other devices like this, like the PreSonus fader port or Studio Logic SL Mix Phase. There are also smaller form factors like this single strip device from Behringer. Behringer also has the big X-Touch Mackie compatible controller, and there are also unusual form factors like this foot pedal device from Nectar, which can be configured to work as a DAW controller as well. And there's also software like TouchDAW, which is an Android program, but you can get similar apps, of course, also for iOS. Okay, let me quickly go over the Mackie Control Protocol. I won't go into much detail here, but just that you have a basic idea of what this is all about. So MCP, Mackie Control Protocol, is a subset of MIDI. And the devices which speak this, the Mackie compatible devices, are usually hardware, as we've seen, but they can also be implemented in software, like the TouchDAW application, which I will be using later because it's easier to record. So you have a device which has two-way communication with your DAW program or whatever application you're using on your computer. Typically these devices have some faders which are transmitted as pitch band messages, other encoders, and the big jog wheel, which are transmitted as sign bit encoded relative control changes. These are typically used to control volume, pan, playback position, and whatever else your DAW is doing. But typically these kind of mixer-like controls, because DAW programs, we all know that a big part of that is mixing stuff, and so it makes sense to have dedicated controls for this. There are also typically various buttons on these devices which get transmitted as note messages. So if you're not careful, then you might hear those notes actually if you have some kind of synthesizer, which then you need to make sure that the Mackie control messages are transmitted on a separate MIDI port so that they don't mix up with any other MIDI inputs that you may have. Then you have the back channel, which is application to device. So this is also known as feedback. So the same kinds of pitch bend and control change messages are sent to the device to set fader and encoder values and the button states. These are again transmitted as note messages. Then there are also some special MIDI messages like aftertouch, which is used to transmit meter values. So if you have some kind of meter strip on your device, then you will be able to control the volumes of the various channels that way. And there are some dedicated control change messages to transmit a time code so that you can see musical time or wall time on the device. The device needs to have some kind of display for that. And another important thing are the scribble strips, which we'll see in a moment. Those are encoded using sysx messages and have some information about which tracks or other elements of the interface you're looking at, so that you know which strip controls which track. Good. Let's have a quick look at how this stuff works in practice. I've hooked up TouchDAW on my Android tablet to a DAW program, Ada in this case, running on my Linux computer. And you see TouchDAW on the left and Ada in the background, and on the right I have KMIDIMon so that we can watch what actually gets transmitted if I start operating the device. For instance, if I press play, then you see that a note message is emitted and the playback starts. So we see the meters reacting, and I can press stop again. Then the playback stops, and you see that was another note message. If I move the sliders, you get pitch bend messages. So this is the basic kind of encoding that you had. You can also operate with the encoders. You can operate, for instance, panning, which will be done with control changes in this relative sign bit encoding. And similar encoding is used with the big jog wheel, which I can use to control the playback position. So if I just you see that the playback position moves if I move the jog wheel, and so all these messages are transmitted from the device to Ada. And let's take a look now at the back channel. So let me quickly configure this so that we can have a look at that. So in particular, if we change the tracks which are displayed, which is possible with some buttons on the device, you can see that various sysx data is communicated back. So this has all the data for the scribble strips, so that I see which tracks I now have on display, and I can move back. And you also see that the fader positions and the encoder positions are transmitted as well. So this is what goes back from Ada in this case, or any kind of application which speaks the Mackie control protocol to the device. All right, let's get back to the topic of this talk. We've seen how MCP devices can be used to operate a DAW program, and now we're going to take a look at how this works with Pd-Faust. In this screenshot, you can see a PD patch, which uses various Faust units. You can see these over here. And there are a couple of other interesting elements here. For instance, these GUIs for the various Faust units here, which is just a synth effects chain, are over here. These are automatically generated, so you don't have to do anything special to get these. And up here, there's a little MIDI and OSC sequencer application, so that I can just push a button and have some MIDI playback and don't have to operate it myself. The rest of the patch is just a normal Pd-Faust patch, but down here is the actual Faust MCP unit, which does all the translation from the MCP device to the Faust units. Let's take a closer look at the Faust MCP unit. The problem that we're trying to solve here is that if you have a Pd-Faust patch, you often have lots of Faust units, and each have their own MIDI controls. We want to have something which automatically assigns these controls to different banks on an MCP device, to different banks of 8 controls each, to the faders and encoders of an MCP device. And this is what this abstraction does. The abstraction itself has a couple of GUI elements which allows you to do some basic manipulations right there in the patch. So you can switch banks there. And in particular, it also shows a facsimile of the scribble strips. In case your MCP device doesn't have scribble strips, you can see them there. And the rest of the operation of Faust MCP is done behind the scenes. So it will connect to the MCP device on the MIDI port that you give it as an argument. I've chosen port 2 here. So the MCP device then needs to be connected to that second MIDI port of PD. And incoming data is then mapped to the Faust MIDI controls and vice versa. All this happens fully automatically. So the Faust MCP abstraction takes a look at the actual Faust units and determines which MIDI controls are there and will map them to different banks on your MCP device. There's also mapping for arm, mute, and select buttons, so that you can do some control there, enable and disable units and arm them for recording. And there are some playback controls which connect to the MIDI OC sequencer abstraction in the patch. And it also provides feedback to the MCP device. So if you change any parameter values on the PD side, it will be reflected on the MCP device. So faders will move and encoders will change their positions and so on. And of course, important kind of feedback is the scribbled strips will have some information about the Faust units. What you can see here is the Faust code of the subtractive synth units that I'm using in this example. I don't want to go into all the gory details here, but you can see that the main Faust program is here. So we have some sawtooth oscillator, which is passed through a filter. An envelope is applied to it. We have volume and panning. So we get a stereo signal out of that. That's just the main program. Details are a bit more complicated, but you can look at the code on GitHub. The central part of this subtractive synthesizer is the low-pass filter. I've taken a tweaked Butterworth filter design, which I found on musicdsp.org, which has the various filter parameters, which I've just written down here, and then have a standard feed forward and feedback parts of the filter. So this is the low pass filter which gets used in the subtractive synthesizer. But the interesting part for our purposes is the controls. So we have these filter controls here, the resonance and the cutoff frequency of the filter, and these what is called metadata in Faust lingo are these designations here in square brackets. So we see that we have an assignment of various control changes to these parameters, controller 20 and 21 in this case. You can choose these any way you like. They will determine the order of the controls on the surface, but otherwise you're free to choose them any way you want. Where in the subtractive synth example, we also have these volume and panning controls, just for illustration, and then the voice controls of the synthesizer itself, which determine which note is played, which don't need any special MIDI designation here. So these are the parameters that we will be able to control via the control surface. There are a couple of other parameters. This is only a abridged version of the code. But just to give you an idea how you configure this in the Faust program. Okay, let's give it a go then. As you can see, we have touched or connected to PD here. I've done that via USB. So there are other possibilities. You can use Rui's QMIDINet or David Moreno's RTP MIDI-D to transmit MIDI data over the local Wi-Fi network, but here I'm just using USB, which is the most direct connection, and I've hooked this up to PD's second MIDI port, which is then all this MIDI data is then handled here in MCP2. And you can see the MIDI controls in the PD main window. If I quickly scroll through here, you can see all the units there and all the control changes that it understands. And these will then be translated automatically to MCP data and vice versa by the Faust MCP abstraction down here. And so if I, for instance, if I start changing the volume here, that gets transmitted and to the MCP device, and you can see that the faders and the encoders follow suit. I've implemented Faust MCP in that way because there are some MCP devices which only have encoders, others may have only the faders, so you can use either of these interchangeably depending on what you have on your device, and if you have both, then they will be in lockstep. This also works if I reset the unit, then it will be back to its default setting again. So these are the most basic controls that I have, so I can change all the parameters which are MIDI mapped. And as I remarked previously, the playback controls will also map to the corresponding controls in this little MIDI OC sequencer applet. So if I push play, you will hear some music. And you will also see some automation data kicking in, which is also OC automation data that I recorded previously. You can do this with Pd-Faust to have some kind of basic automation control. And of course I can also operate the sliders in real time. Let me quickly start this again. So I can of course also switch banks to get to other controls from other Faust units. For instance, here I have the controls for the chorus and the reverb effect. And here is the final stage, which is labeled FX3 over here. And you can see that the passive controls, which are also displayed here, are also displayed as meters on the Android device. Yeah, so that's about it. Um, You have playback controls, you have all the faders working, you have the scribble strips, you have ARM record, you have reset capability for the Faust units. You can enable and disable them. I should maybe show that one more time. So if I press mute now, then the entire synth unit is muted and you don't hear anything anymore. And if I unmute it, you can hear that unit. You can also do that with effects unit, which will effectively bypass them. So you now hear the sound without all the effects. And let's unmute that again. So also the jog wheel works to change the playback position, and this is what you get. So you have automatic mapping of MIDI. That's the most important aspect of it, so that you don't have to configure your controller for certain Faust units. This will all the mapping will be done automatically for you. Okay, there you have it. Let me quickly conclude with some remarks. First, I've tested these with all the MCP devices that I have available, Behringer X-Touch, also the small one, the X-Touch 1 and the X-Touch Mini, with the Studio Logic mix phase and with the Korg Nano Control and U-Matic's Touch Door, which we've seen in this presentation. But I expect this to work with any MCP compatible device, of course, according to the limitations and capabilities that your device has. The software itself, Faust MCP, still has some limitations and bugs. I won't go into these here because they're rather obscure, so you can find these in the paper. It's perfectly usable right now, but I consider it more as a proof of concept. The most strict requirement right now is that this only works with Pd-Faust, which is the environment that I used here. And this is written in my own pure programming language, which unfortunately hardly anybody seems to use. So there's also the problem that pure is still stuck on old LLVM version, which doesn't work very well with newer LLVM versions, and that is a problem because it makes some other externals crash in PD if you try to use them alongside each other, and that's not a good thing, obviously. So I will get around this by rewriting Faust MCP for the new Pd-Faust Gen 2 external, which is a souped up version of Pierre Guyot's Pd-Faust Gen. And this is slated to become the replacement for Pd-Faust, because with Pd-Faust Gen 2 I now have basically all the features of Pd-Faust in the Pd-Faust Gen external, and this is much easier to use and also to get up and running because it doesn't require pure. And so this is still in the future right now, but I expect to have this finished by sometime next year. Okay, as usual, thanks for listening, and my future self will take it from here and hopefully be able to answer all your questions. Thank you very much.